Hello everyone, today I will be talking about our work on scalable metadata hiding for privacy-preserving IoT system. My name is Xunyang Chen, and this is a joint work with David Hertz, Rahul Chatterjee, and Ernest Fernandez. In today's IoT ecosystem, it is very common for users to own multiple devices from different vendors, which makes device management a difficult task because users must communicate with each vendor individually to interact with their smart devices. To simplify this, many users turn to integration solutions such as Alexa, Google Home, or IFT. We refer to these services as IoT integrators. They serve as a middle layer to provide a centralized interface for device management. Now, users send all their messages to the integrator, and the vendors also receive user messages from the integrator if they are compatible with the corresponding protocol. However, this convenience comes with a privacy cost. The integrator, by their virtual office role, gains comprehensive access to all user device interactions. Given the nature of many IoT devices, this interaction data can be exploited to infer sensitive information, such as the user's sleeping pattern or daily routines. So, how do we design a privacy-preserving IoT system to safeguard such information? The challenge here is that even with end-to-end encryption, user activities can still be leaked through metadata. Let's consider this example below. The user sends a log command to their smart door lock, and this command is encrypted using a key shared only between the user and the door lock. However, the integrator still sees that the user's command goes to the company August, which unfortunately in this case is a vendor who only manufactures smart door locks. So the integrator knows the user is either trying to lock or unlock their door. Combining with other information, like the message time, the integrator will be able to have a good guess at what the user is doing. Therefore, we designed a system called Mojito to provide metadata hiding properties for IoT system. In this talk, I will only cover how Mojito delivers user messages to the devices in a privacy-preserving manner, but Mojito also supports sending the device messages back to the user, which you can find more details in our paper. At a high level, we have two security goals. First, for the integrator, when it receives a message from the user, it should not learn which vendor this message goes to. Second, for the vendor, when it sends a message to a device, it probably already knows that which user bought that device in the first place. So instead, we let the vendors to send messages to every device it owns in each round. But the vendor should not learn which messages are actually from real users. Before we go into details of Mojito, I want to discuss why we need to design a new system. Why can't we just use some existing solutions? One common approach to provide privacy is to hide the user identity, but these solutions usually require another third party to sit in between users and the integrator, which makes them hard to be adopted. Alternatively, we can turn the integrator and the vendors into a mixed net. However, a mixed net requires peer-wise communication, whereas there is usually no direct communication channel between two different vendors. There are also other existing anonymous communication protocols that could fit into the IoT model, but they can be unfair to small vendors which only carry a fraction of the larger vendors' traffic, or they may have low throughput, which makes them inefficient when handling concurrent requests. Now, I will show how our system, Mojito, protects metadata from the integrator. When a user wants to issue a command to their device, they will need to encode the vendor ID, device ID, and the command into their message, and then perform a two-layer onion encryption. The inner layer is encrypted with the integrator's key, while the outer layer, for simplicity, we assume that it will be encrypted with a particular vendor's key. The integrator will gather all user messages in each round, send it to that particular vendor to decrypt and then shuffle. That vendor will send the shuffled messages back to the integrator, which can finally decrypt the inner layer to get the plaintext message. In this way, it will learn which messages goes to which vendor because of the encoded vendor ID inside each message, but the integrator doesn't learn which user originally sent which message. The second step is for the integrator to forward these messages to the corresponding vendors. Suppose that in this round, it needs to send 2 messages to vendor 1. Obviously, it can't send these messages directly, otherwise the vendor will know that device A and B have received commands from real user. In Mojito, we use a cryptographic protocol called the Oblivious Key Value Store. Basically, this protocol will encode the device ID and command pairs into a table using a technique similarly to cuckoo hashing. For each message, we will compute 2 hash values for the device ID. Let's say that for device A, the hash values are 0 and 3. Then it will store the secret shells of the command X into the corresponding location in the table. Then let's say for device B, the hash values are 0 and 2. Since index 0 already has a value, we can just compute the secret shells for command Y in index 2, so that when we add these 2 shells together, it equals to command Y. Once we complete this table, it will be forwarded to the vendor. The vendor can then use its own device IDs to query. If the device ID is used to encode this table, like device A's ID, the vendor will be able to recover the original command successfully. But if this device ID has not been used to encode the table, like device C's ID, then the vendor will just get some random data. So you can observe that if we make command X to be some end-to-end encrypted value between user and devices, then command X will also appear random to the vendor. In this way, the vendor can't tell which device received real messages and which device had received some random bytes. Okay, so even with all the protocols that I described earlier, we are still vulnerable to one type of attacks, which is the cross-round intersection attack. Well, normally with a large anonymity set, it is very hard to carry out intersection attack against this type of system. But there's a common scenario in IoT world that makes us vulnerable. Imagine that in certain round, only 2 users, Alice and Bob, participate, and in those rounds, the integrator always observes that one message goes to vendor X and one message goes to vendor Y. Then, in a new round, Charlie buys a new device and joins the system. Now, there are 2 messages to vendor X and 1 message to vendor Y. The integrator can tell with very high confidence that this new user, Charlie, is communicating with vendor X, and thus our security goal is violated. To defend against intersection attack, one common approach is to let users send cover traffic. But in the IoT world, users are just smartphone apps that should not be online all the time. Instead, Mojito takes a different approach. We let the vendors that shuffles the messages also inject cover traffic, and we build a protocol using private sum to inform the vendor how many messages to inject. For performance evaluation, we focus on the throughput, since IoT services often need to handle lots of concurrent messages. Compared to the state-of-the-art general-purpose system that provides similar security guarantees, Mojito is able to achieve up to 600 increase in throughput. Additionally, The throughput does not change no matter how many messages we put into each round, making the protocol very scalable. Finally, Mojito does sacrifice the built-in single message latency, since we are using a round-based approach, but all messages will have similar latencies, whereas in other systems, the message latency usually scales with the number of concurrent messages. So that's all I want to talk about today. In summary, we built Mojito to incorporate the integrator-centric IoT system. We make metadata protection as the top priority, while maintaining a high throughput to ensure it can accommodate the unique challenges brought up by the IoT use case. You can read more details about it in our paper, or if you have any questions, please feel free to contact me. Thank you.